So good morning, everyone, and welcome to this lecture. In this lecture, we are going to finish heat and thermodynamics once and for all. We are dealing with radiation, and in the last class, the last thing that we saw was Wien's displacement law. We saw that as you increase the temperature of a body, the wavelength at which it emits maximum energy decreases. Lambda maximum into T is a constant. That is your Wien's displacement law. We had seen a couple of examples. Let us move ahead and take this question. I'm expecting a question from this category. So this is the next question. The energy spectrum of a black body exhibits a maximum around a wavelength lambda naught. The temperature of the black body is now changed. The energy is maximum around a wavelength 3 lambda by 4. What is the power radiated will increase? I'll give you 2 minutes to give me the answer. Option A. How did you get option A?
The E is directly proportional to T power 4.
E is directly proportional to T raised to the power 4 and lambda maximum into T is constant. Original lambda was lambda naught, and now it has become 3 lambda by naught, so the temperature will become 4 by 3 times of T naught. Yes or no? So the energy will become 4 raised to the power 4 divided by 3 raised to the power 4 of the original energy. It will it changes by a power of 4, and therefore the correct answer is option A. Do we understand this?
Yes.
I've seen a couple of questions comes from assertion and reasoning. So this is a question from assertion and reasoning. Consider the following statements. A blue star is at a higher temperature than red star. Wien's law states that T is inversely proportional to lambda m. Of these statements, both assertion and reasoning are true. I hope you know assertion and reasoning. And R is the correct explanation. Both are true, but R is not the correct explanation. A is true, R is false. Both A and R are false. A is false, but R is true. I'll give you 2 minutes to give me the answer. Option A, and I've already given you the example of blue flame and red flame. Your gas stove has blue flame, that is at a higher temperature. If you put water, it becomes orange or red. We understand this, yes or no?
Yes.
This is the next question from previous year IIT. The black body is a temperature of 2880 Kelvin. The energy of radiation emitted by this body with wavelength 499 nanometer to 500 nanometer is U1. Between 999 nanometer and 1000 nanometer is U2. Between 1499 and 1500 nanometer is U3. The Wien's constant is given. Which option is correct? I'll give you 2 minutes to do this. That is absolutely correct. From lambda into T is constant, which is B. You can find out the maximum. You can find out the maximum wavelength. T is known. You can find out the wavelength for which maximum energy is given, and I think that is coming as 1000 nanometers. Yes or no?
Yes.
So at 10,000 nanometers, it will be maximum. Which option tells us that it is like this? This is option 2. U2 will be greater than U1. If you want, you can look at this diagram. The diagram of this, the energy spectrum of this black body will look something like this. And I hope you understand the rest of the things. Yes or no? No or yes?
Sir,
Yes.
energy of radiation emitted never be equals to zero, no, sir? Or maybe it can be equals to zero.
I don't understand what you are saying.
Sir, can energy emitted maybe zero equals to zero?
Which
Or
energy? Energy, if a body is at a temperature more than 0 Kelvin, it will always emit energy. What is your doubt?
sir, my doubt is energy of radiation emitted can be equals to zero or not.
Read the statement. Prevost theory of exchange. What was the first statement?
All bodies radiate thermal radiation at all temperatures.
Now ask your doubt. What is your doubt?
Mm,
What is your doubt? Yes, what is your doubt?
nothing. Like means it cannot be equals to zero.
Because if it is equal to 0, that means what?
The bodies will not emit radiation.
Think again. If the energy emitted by a body is 0, what does that imply?
Okay, it's perfectly it's black body which absorbs perfectly.
Take a deep breath. Close your eyes. Think for a moment. And then answer. If a body emits 0 radiation, what does that mean? What does that mean? If a body is emitting 0 radiation.
Sir, the temperature of the body should be less than absolute zero.
Why it is called absolute 0? Why it is known as absolute 0? Why? Why that temperature is known as absolute 0? Because nothing less than that is possible. If a body is not emitting radiation, it means the temperature is absolute 0, which is also not possible. Forget about less than absolute 0. I don't know from where you are getting all these fancy ideas of temperature getting less than absolute 0. Arey, absolute 0 is not possible. Absolute 0 is not possible. Therefore, it is not possible for a body not to emit radiation. And that is the first line that is there. All bodies radiate thermal radiation at all temperatures because temperature cannot be 0 Kelvin. That is not possible. It was the first line when we started everything. 0 Kelvin is not possible in this universe. And therefore, all bodies emit thermal radiations at all temperatures. That takes us to the next question. I will not waste any more time on this. What is the graph for frequency, maximum frequency, and time for a perfectly black body? Which is the graph? A, B, C, D. Between the graph between the frequency of maximum energy and absolute temperature on the Kelvin scale. 0 of this scale is not possible because we have not achieved that temperature. Even in the vastness of space, we don't see absolute 0 temperature. We don't know what happens at absolute 0 of temperature. Therefore, all bodies emit thermal radiation at all temperatures because the temperature cannot be 0 Kelvin. Yes, which graph represents this one?
Oh, B, sir.
B graph, because lambda m is inversely proportional to T and V is equal to F lambda. So maximum frequency will be directly proportional to T and the graph would be B. Do we understand this, or this has gone above our heads? Saying bye bye, bye bye, I'm going bye bye, bye bye, bye bye.
Understood, sir.
Do you understand why it is known as absolute 0? Do you understood this? It has gone above
Yes,
our
sir.
heads. Thank God! God is almighty. And I thank him for his kindness that you remember this. Absolute 0. Now comes the next part of this chapter, which is known as Stephen's law. Some people also call it Stephen Boltzmann law because it was proved by Boltzmann. What is this Stephen's law? Huh? Thermal radiation or radiation, or what should I say? Emissive power. Do you remember this emissive power? E. What was emissive power? Do we remember emissive power? Or we have forgotten it like absolute 0. What is emissive power?
Sir, relative.
Well done, we have forgotten it as expected. I would be surprised if you remember it. I am not surprised when you forget it. Just yesterday we had done this. And today we are chilling out, forgetting everything, and still coming in the class. Remember, once you come in the class, apart from your bodies, you have to bring your mind and soul and memory also. You cannot behave like Gajini of Amir Khan. It only looks good in movie. It is useless fellow. You cannot become Gajinis. The only thing that you have to forget is the habit of forgetting things. And I told you, the only thing that you have to remember in this chapter is the definition. And if you don't remember them, bye bye. Bye bye. Bye bye happens. Bye bye. Bye bye. Bye bye happens. Bye bye. Yes, do you remember it now? Even after reading from the notes, you don't remember. Well done.
It is the energy emitted per unit time united.
If you don't remember it, my dear friends, what will happen? Nothing happens. Sorry to say. Anyway, since we have remembered this is what Stephen's law says. The radiant power or the radiant energy or the thermal radiation or radiation energy or whatever emitted by a perfectly black body, Kali body, per unit area, per unit time, that is emissive power, is directly proportional to the fourth power of T. We have seen this emissive power of a black body per unit area, per unit time, directly proportional to T raised to power. We have done questions on this, my dear friend Stephen Straw. Emissive power. Or I can write this is equal to sigma T raised to the power 4, where this sigma is a constant which is known as the Stephen's constant. Stephen's constant. Stephen's constant. Stephen's constant. Stephen's constant. And remember, it's a unit and dimension, because most of the question in units and dimension in JEE Advanced come from this Stephen's constant. M t minus 3 theta minus 4, because t raised to the power minus 4. This is Stephen Boltzmann law, proved by Boltzmann, given by Stephens. This law is only valid for a black body, Kali body. For normal bodies which are not Kali, which are of some other color, then what happens? For any other body, if it is not a black body, how will I get the formula for any other body which is not a black body? Huh? I will just multiply this by E. Small e. What is small e? This small e. This chota sa e. This chota sa e. What is this chota sa e? Huh?
Emissivity.
Thank God. Emissivity is written in the statement. That is why you remember. I am not surprised. Chota e is emissivity. Bada e is emissive power. Now, this is the energy or radiations or thermal energy emitted per unit area, per unit time. If I multiply it by the area and I multiply it by the time, this is the formula for thermal radiations emitted by any body as a function of time or a function of area or whatever you say. Small t is time here, capital T is your absolute temperature. Absolute zero cannot be possible. All bodies emit thermal radiation. Do we understand this, or this is going above our head saying bye bye? I'm going bye bye. Bye bye. हो गया bye bye? Huh?
No, sir.
पक्का?
Yes.
Then I will give you a minute. Okay, I can put one more thing here. Now remember, this is, just listen to me first. There is no point of writing, because you don't remember things. What will you do by writing? You will not be able to find them where you have written, because you don't remember them. This is the emissive power. Dung 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 dung. It is emitting energy. Fui 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 fui. But the same time when it is emitting energy, it is also doing some more thing. What? This body. This is not. This looks like a black, but it's not a black body. It is emitting energy. At the same time, it is also doing what? Huh? I don't know, sir. I am not a black body. Even you are doing it right now. You are emitting energy, at the same time you are
Radiating.
radiating is emitting.
Absorbing, sorry.
Yes. At the same time you are absorbing energy. which is emitted by nearby bodies. Now, instead of thinking it of as nearby bodies, you can say that which is radiated by the surroundings, or if the surrounding is at a temperature T naught, you are absorbing energy from the surrounding and you are radiating or emitting energy of your own. Do we understand this? So you are absorbing energy and you are emitting energy. The difference between the two will be the net energy absorbed or net energy emitted. If your temperature is more, you will radiate more energy and absorb less. If your temperature is less, you will radiate less and absorb more. And that is how your temperature increases or decreases. Remember this?
Yes, sir.
Prevost theory of exchange. So, if you are surrounded by a surrounding of temperature T naught, you are radiating as well as you are absorbing. The net energy lost by you will be E sigma T raised to the power 4 minus T naught raised to the power 4. This is the energy radiated or lost per unit area per unit time. Do we understand this?
Yes.
Now I will give you 2 minutes, not for keeping silence, but for noting down what we have done. Now, life goes ahead. Now, if you are having a temperature more than the temperature of the surroundings, then what will happen? You will start to lose heat or heat energy. Yes or no?
Yes.
Now, if this is the energy per unit area per unit time, if I multiply it by area and divide it by multiply it by area, that will give me the rate of heat lost dq by dt. Yes or no? Heat current. Remember heat current, dq by dt. It is not current because this is not conduction. This is radiation. So, if I am at a temperature T, capital T, and surrounding it at a temperature T naught, I will be losing heat by this rate. I just multiplied the above equation by A. Do we understand this?
Yes.
dq by dt will be equal to this. Yes or no? No or yes? Do we understand this?
Yes, sir.
Now, if I go back to that first thing, calorimetry, this dq by dt will be mc or m capital C, specific heat capacity dt, d theta by dt. Yes or no?
Yes, sir.
mc delta theta. Do you remember?
Yes, sir.
Now, from both the equations, what you can determine is the rate of fall of temperature, which is known as the rate of cooling. So now you can have this rate of cooling coming in. Rate of cooling means rate of change of temperature, and the rate of change of temperature for a body of temperature capital T kept in a surrounding of temperature T naught. E emissivity, A area of cross section, sigma Stephen's constant, M mass of the body, C specific heat of the body. Do we understand this? Yes or no? No or yes?
Yes, sir.
I'll give you 2 minutes to note this down. So, we have seen this revolutionary formula. Then we can note down these simple things from the formula. When a body cools by radiation, The rate of cooling d theta by dt depends on the nature of the substance E, depends on the area, directly proportional to area, inversely proportional to the mass. Yes or no? No or yes?
Yes.
Then it depends on the temperature of the surroundings, it depends on the specific heat, and it depends on the temperature of the body itself. Yes or no? No or yes? Do we understand all these points?
Yes, sir.
You'll have to remember them. I'll give you 2 minutes to note them down. Fatafat. So what we have seen is the rate of rate of cooling or rate of change of temperature. Now we have seen that it depends on sigma E, A, M, C. Now there might be some tricky points here. So you can note down some tricky points, and this is the first of those points. If all the parameters are same, rate of cooling or rate of heating, RF and RH, rate of cooling and rate of heating will be maximum for a flat surface. The surface is flat, it will cool down or heat up quickly. You have seen that, yes or no? That's why nowadays we have flat bottom cooking utensils, because heat is evenly distributed and it heats up faster. Do we understand this?
Yes, sir.
If you have a solid body and a hollow body, same mass, same everything, same material, same specific heat, same area, which will cool down faster, the solid body or the hollow body? The hollow body will cool down faster. Do we understand this?
Yes, sir.
So remember this. Last point, and then I'll give you time to note this down. The rate of cooling or rate of heating is inverse. Everything is same for two bodies with different specific heat, S1, S2, and S3. All the other parameters being same. Time for cooling will be directly proportional to. I mean, there are different conditions that can be made. Here they have taken the condition where everything is same and specific heats are different. Do we understand this?
Yes, sir.
Note this down, then we will solve some questions based on this. Then let's move ahead and solve a couple of problems on this concept. Here is the first one. Two black metallic spheres of radius 4 meter at 2000 Kelvin and 1 meter at 4000 Kelvin will have the ratio of energy radiations. Give you a minute. How did you get 4:1?
Sir,
Huh?
it is Sir, it is
Yes.
directly proportional to area and
Energy Q per unit time dq by dt. Yes. It is directly proportional to E sigma A.
A T power 4.
So the answer
Sir,
is 4:1.
area is 4 by 3 pi r cube.
Wow. You need to take deep breaths. Cool down. Think again. And then give me the answer. What is the area?
4 by 3 pi r square, sir. Sorry, 4 pi r square.
See, when you think again, you get the right results. So what is the final answer now?
1:1, sir.
See, the answer has drastically changed from 4:1 to 1:1. You think correctly. Area is directly proportional to r square. Radius is 2 times. Radius is 4 times. 4 square, 16. Temperature is half. 2 raised to the power 4. 1:1. You will get. Simple question, my dear friends. Take a deep breath. Do not answer in a haste. These questions, you will see them in your exam 4 days from now. You have to take a deep breath and then give the answer. This is the next question. I'll give you a minute. Take a deep breath and then give me the answer. Option D, sir. It is absolutely correct, sir. The rate of heat gained or heat lost, Q, is directly proportional to T raised to the power 4 minus T naught raised to the power 4. You put the values, you get the answer, and you stay happy. Next one. Take a deep breath, give me the answer, and stay happy. Power. Delta Q by delta T is directly proportional to A E T raised to the power 4. Yes or no?
Yes, sir.
Both are at the same temperature. Radius. So it is directly proportional to radius square. Yes or no?
Yes, sir.
So the radius are in the ratio of 1:2. So this will be in the ratio of 1:4. So the correct answer is 1:4. Do we understand this?
Yes, sir.
Next question. Same concept. Power is equal to E A sigma T raised to the power 4. Power is same. So the ratio of radius will be uh, inversely proportional to temperature square. Yes or no?
Yes, sir.
So the answer would be option A or C. Option A, inversely proportional. Correct?
Yes, sir.
Okay, so I think you have done this. Now let me give you this one. Might require some calculations. You have 2 minutes to do this. So how are we supposed to do this? This is the rate of change of temperature. If I talk about rate of change of temperature, it is equal to E sigma AE divided by M into C T raised to the power 4 minus T naught raised to the power 4. The change in temperature is same. The surrounding and the body temperature is same. The specific heat is same. E is same. Sigma is same. It is dt is proportional to 1 by dt is proportional to A by M. Or you can say dt will be proportional to mass divided by area. Mass is density multiplied by volume divided by area. Volume of a cube is a cube. Area of a cube is 6a square. I can write it as a square multiplied by density. So you can see that the time taken will be directly proportional to the edge length of the cube. Edge length of the cube from 1 centimeter has become 2 centimeters. Therefore, the correct answer is 200. This is the rate of cooling. Do we understand this?
Yes, sir.
Great. Here comes the next question. And I hope I can get an answer for this one. Two metallic sphere S1 and S2 are made up of same material and have same surface finish. The mass of S1 is 3 times of S2. Both the spheres are heated to the same high temperature and placed in the same room, having same lower temperature. Thermally insulated from each other. The ratio of initial rate of cooling is how much? So how are we supposed to do this? The rate of cooling d theta by dt is equal to E sigma A by mc t raised to the power 4 minus t naught raised to the power 4. This is same, this is same, this is same, this is same. So rate of cooling for these two spheres will be proportional to area, which is proportional to r square, mass, which is proportional to r cube. So it is inversely proportional to 1 by r. The ratio of their radius, same as the previous question. Inversely proportional to r, rate of cooling. Now we just have to find the ratio of r. Mass of S1 is 3 times. So 4 by 3 pi r1 cube into rho is equal to 3 times 4 by 3 pi r2 cube into rho. From here I can find out the ratio of r1 by r2. r1 by r2 will be 3 raised to the power 1 by 3. So rate of cooling of 1 divided by rate of cooling of 2, 1 will be 1 by 3 raised to the power of 1 by 3. So that is the
Sir,
answer that we were looking at.
one doubt, sir.
Yes.
Sir, same identical surface finish means surface area is not same, sir.
Surface finish, they said. Did they say area? Did they say area?
What
You can
what
assume,
it
you can
means, sir?
assume anything from your imagination. Surface finish means sigma means E is same. Surface finish. What has it got to do with area? You have assumed something on your own. Don't assume anything on your own. This is the next question. A sphere, a cube, and a thin plate, all of the same substance and the same mass, heated to 400 degrees, 200 degrees Celsius, and placed in a room. Which one loses? Remember, for a given volume, cube has the minimum. For a given mass, cube has the minimum area. Do we remember this? For a given volume, for a given length, if you are given a length L, circle has the maximum area. For a given volume, sphere has the minimum area. You must remember that. Do we understand this? If you are given a volume, which is the body that you can create, which has the minimum area, that is a sphere. Now, we have seen rate of cooling, dt by dt, E A sigma, E A sigma by mc t raised to the power 4 minus t naught raised to the power 4. Mass is written as volume into density. Mass is same for each and every one. Everything is same. So this depends directly on the area. For a given volume, sphere has the least area, and therefore the answer would be A. The rate of loss of heat for the sphere would be minimum. Do we understand this? Yes or no?
Understood, sir.
I'll give you 1 minute to note it down. The next heading is the last heading for this. And we ended with the famous Newton's law of cooling. What is this Newton's law of cooling? Now, this Newton law of cooling, remember, is only valid for a small temperature difference, 5 degrees, 10 degrees, 15 degrees, not more than that. What does this Newton law of cooling state? For small temperature difference, 5, 10, 15 degrees, for small temperature difference, the rate of cooling is directly proportional to the temperature difference of the body with the surroundings. That means d theta, the rate of cooling is directly proportional to the temperature difference. Just forget about this. The rate of cooling is directly proportional to the temperature difference, or you can say d theta by dt is directly proportional to theta minus theta naught. Well, what is theta? What is theta naught?
Theta is temperature of the body and theta naught is temperature of surroundings.
So d theta by dt will be minus k into theta minus theta naught. Do we understand this? Remember the value of this k, and sometimes we might encounter a question where this value of k is this. Now this value of k is determined from that Stephen's law. You take the temperature difference to be small and then you can derive it. The derivation is not a concern for you. So this is the original form of Newton's law of cooling. Just give me a minute. I'll give you time to write, then you write. Let me first finish what I have to finish. Newton laws of cooling. Now you can easily integrate this equation, yes or no? From initial temperature theta 1 to any temperature theta. Once you integrate this equation, you will end up with this one. Theta at any time t will be equal to theta naught, where what is theta naught? Theta naught is the surrounding temperature plus theta 1 minus theta naught e to the power minus kt. This is the original form of Newton's law of cooling. This is the original form of Newton's laws of cooling. You can also write this equation in this way. You can also write this equation in this way. Ln of theta minus theta naught divided by theta 1 minus theta naught is equal to minus kt. I'm writing in the form of ln because in the form of ln this becomes a straight line. Do we understand this? Equation between ln and this will be a straight line equation. Do we understand what I'm saying?
Yes, sir.
If you draw a graph, this is an exponential graph. I hope you understand. The graph between temperature of the body and time would be an exponential graph, which would be like this. Do we understand this? This is known as Newton's laws of cooling. I'll give you 2 minutes to note it down. And you can note down these limitations of Newton's laws of cooling. The first is the difference in temperature between the body and the surrounding must be very small. It only considers heat loss due to radiation, and the temperature of the surrounding must remain constant. Remember, these three are very important terms. Please note them down. Now, sometimes what we are going to do, instead of using the original form of Newton's laws of cooling, we are going to use the approximate form. Now, what is this approximate form? In the approximate form, what we have is d theta by dt. The rate of change of temperature is written as minus k times theta average minus theta naught. Where what is this theta average? This theta average is taken as theta 1 plus theta 2, initial temperature, final temperature divided by 2. So the approximate form of Newton laws of cooling start to look like this. Theta 1 minus theta 2 by t will be equal to minus k. Just you have to put minus k here. Minus k into theta 1 plus theta 2 by 2 minus theta naught. Do we understand this?
Yes.
This is the approximate form of Newton laws of cooling. The real form, you can also write real form here so that you have real form of Newton laws of cooling and write it on this side so that you can compare the real form. D theta by dt is minus k times theta minus theta naught. When you integrate this equation, you will get theta will be equal to theta naught plus theta 1 minus theta naught e to the power minus kt. You can write it like this: theta minus theta naught is equal to theta 1 minus theta naught e to the power minus kt. In this way, or you can write it as ln of theta minus theta naught divided by theta 1 minus theta naught is equal to minus kt. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. Okay, then these are the various curves that I had promised. Curve between temperature and time, we have already seen this. Curve between rate of cooling and the body temperature from approximate form. Between rate of cooling and theta minus theta naught. Between log of theta minus theta naught and time. This is from the original graph. Do we understand all these curves? Yes or no? I'll give you 2 minutes to note it down. Then let's move ahead and solve a couple of questions. This is the first one. A cup of tea cools from 60 to 80 degree. 80 to 60 in 1 minute. Ambient temperature is 30 degrees. From 60 to 50, how much time will it take? So we are going to use the approximate form. Approximate form says theta 1 minus theta 2 by t will be equal to minus k times theta 1 plus theta 2 by 2 minus theta naught. Yes or no? In the first case, it is 80 minus 60 divided by 1 minute. So I can write it as 1. My answer that I will get will be in minutes. Or I can write 60 seconds so that the answer that I get will be in seconds, will be equal to minus k. Theta average will be 70. 70 minus 30. Do we understand this? Yes or no? In second case, I will write it as 60 minus 50 divided by t will be equal to minus k times 60 plus 50 divided by 2. That will be 55 minus 30. You can divide the two equation and get the value of time. Can you tell me what is the value of time? I'll give you 2 minutes to give me the answer. The value of time that you are going to get will be approximately coming as 50 seconds. Do you get how do we get this? Then we can solve this question. I give you 2 minutes, 3 minutes. To solve this, the body takes 3 minutes to cool from 62 to 61 when the surrounding temperature is 30 degrees Celsius. Find the time taken to cool from 46 to 45.5. So how are we supposed to do this? We are going to make the first equation. 62 minus 61 divided by T will be equal to minus K. 62 plus 61 divided by 2 minus 30. In the second case, 46 minus 45.5 divided by small t will be equal to minus K. 46 plus 45.5 divided by 2 minus 30. You will have to solve these two equations and get the answer. The answer that is given in the book is equal to T. So I hope you are getting the same answer. Do you understand this? Yes or no? Just have to apply the same equation. Last question for today, and for thermodynamics, I'll give you 2 minutes to solve this. Same question, but here you have to find out the temperature of the surroundings. I'll give you 2 minutes to do this. So how are you supposed to do this? 60 minus 50 divided by 10 will be equal to minus K. 60 into 50, 60 plus 50 by 255 minus 30. Minus theta, the temperature of the surrounding. 50 minus 42 divided by 10 minus K times 50 plus 42. I think the average will be 46 minus theta. From here, you can calculate the value of theta. I think the value of theta is coming as 10 degrees Celsius. Do you get this? Yes or no? Well, then this brings us to an end of this class, an end of thermodynamics. We are done with thermodynamics. In the next class, that is tomorrow, we will begin with electrostatic. Everyone understood this? Yes or no? Okay, then I'll see you tomorrow. Take care. Bye-bye.